Good evening, children. In today's lesson, I'm going to teach you on a chapter of sound. Sound, what is sound? Sound is a form of energy which produces a sensation of hearing in our ears. Sound is produced when a body vibrates. Thus, each sound is produced by a vibrating body. Sound necessarily needs a medium for propagation. When a body vibrates, the particles of the medium also start vibrating. During vibrations, there is a change of kinetic energy into potential energy and potential energy into kinetic energy. That is why we call sound a form of energy. The speed of sound in air is nearly 330 meters per second, and the speed of sound in water is nearly 1500 meters per second, and the speed of sound in iron, which is a solid, is nearly 5000 meters per second. Propagation of sound in air. When a source of sound vibrates, it creates a disturbance in the medium near it. That is, the condition of medium changes. Okay? The disturbance then travels in the medium in form of waves. Now this diagram alongside illustrates the propagation of sound wave. Okay, so it's an example of the propagation of sound wave. In this illustration, we have a metal strip fixed to a base, all right, and we placed it in air. We call this rest position of the metal strip as position A, all right, and then we will make this metal strip to vibrate. Okay, since air particles are all around it, when the metal strip is at rest, the air particles will remain like this. Okay, they will remain in their own place. Then we push this metal strip from the rest position A to B. So it comes to position B. What happens? Then as this metal strip comes to B, it pushes the air particles in this area. So they get pushed and they come closer to each other in this region. So we call this region the compression region. Whereas in the rest of the areas, you'll find the air particles still remain in their own respective positions. Then in the next we find that this compression now from here will be traveling, will be propagating to the next layer, and as they propagate to the next layer, they get pushed to the next layer, leaving an area with few number of particles here. So we have the compression area here, and then the fewer number of particles here, which we call the rarefaction area. Okay, the rest will remain the same. They have not been disturbed. Okay, now when metal strip goes back to A, then what happens is this area now will have fewer number of air particles, because B pushes the air particles now to this area. Okay, so as the metal strip moves to this position C, then this area will also be getting compression, but this area will be left as a rarefaction area. So we have the air particles now to propagate from this area to this area. So we have rarefaction here, compression here, all right, and next it will be compression here, rarefaction here. So that is how we see the propagation of the sound wave in the medium of air. Okay, so the region of air in which the air particles come closer to each other due to the disturbance is called the compression. The region of air in which the air particles become less dense due to the moving away of the cause of the disturbance is called the rarefaction area. Now, one complete to and fro motion of the strip forms one compression and one rarefaction, which together constitute one wave. The terms related to a wave: amplitude. The maximum displacement of a medium particle, of a particle of the medium on either side of its mean position is called the amplitude of a wave. It is denoted by the letter A and its SI unit is meter. Why? Because it's the displacement. Alright. Now this mean position is the one that is the rest position of the particle. Okay. Once you disturb the particle, it will move up and down, or it will move like this, it will vibrate like this, but it will move to and fro. Alright, to and fro. So the highest point that it goes from the mean position, whether it is up or down, or whether it is in the same direction, how much it goes from the mean position, that is what we call the amplitude, which is the maximum displacement. Okay, and remember, being the displacement, it's measured in meter and its symbol is small a. Then we go to the next, that is the time period. The time taken by a particle of a medium to complete its one vibration is called the time period of a wave, meaning the time for one complete vibration. That is what we call the time period. Time period is denoted by the letter capital T and its SI unit is second, because after all it is the time taken. Alright. Frequency. The number of vibrations produced by the particle of the medium in 1 second is called the frequency of the wave. Okay. What is it? The number of vibrations in 1 second. Okay. So for vibrations we can also call it wave. So we can call the number of waves passing through a point in 1 second. That is what is known as the frequency of the wave. So you can define it by either of these two. But remember, in both the cases, it is denoted by the letter F, small f, and its SI unit is hertz. And remember, hertz is 1 by second. Relation between frequency and time period. Frequency is equal to 1 by time period and time period is equal to 1 by frequency. In other words, it means that these two quantities are reciprocals of each other. Now, the next is wavelength. The distance traveled by a wave in one time period of vibration of particle of medium is called the wavelength. Now, please just keep in mind, children, when we talk about the distance traveled by a wave in one time period, we refer to the linear distance. All right, we are not going along with the wave in the waveform, but the distance linearly is what we call the wavelength. And wavelength is denoted by the letter lambda. Remember, lambda is not in itself the word. When we say the distance traveled by a wave in one time period, please don't write lambda. It is wavelength. We use it only for the symbol for wavelength. And being the distance, okay, so its unit is meter. Now, in a longitudinal wave, which usually is the form which sound wave travels, the distance between two consecutive compressions or between two consecutive rarefactions is called one wavelength. Now look at this graph, okay, it will be more clear to you. This is one compression and this is one compression. Distance between one compression to the next compression, these are the two consecutive compressions. So distance between here to here linearly is the wavelength. Okay, so the linear distance. Or we can take from one rarefaction to another rarefaction, and that will be also one wavelength. And the time taken from here to here, this is time period. Okay, now amplitude is this distance. Here is the rest position. This line denotes the rest position of the particle. How much it goes here and how much it goes here, that is known as the amplitude or the maximum displacement on either side of the mean position. Okay, so this is the amplitude and this is the time period. Are you clear, children? We go to the next, that is the characteristics of sound. Two sounds can be distinguished from one another by the following characteristics, that is by the loudness or the pitch or the timbre or quality of sound. Loudness of sound. Loudness is the characteristic of sound by virtue of which a loud sound can be distinguished from a faint sound. Please remember, we use the word loud sound, faint sound, both having same frequency and same wavelength, meaning these two characteristics remain the same, but still we can find out the difference between two sounds by this characteristics. How? The loudness of sound depends on the amplitude of vibration of the vibrating body producing sound. Okay, so amplitude, just now I have explained to you, this is the amplitude. Okay, the maximum displacement from the mean position to this point or from the mean position to this point will be the same. All right, so how much it goes on either side of the mean position, that is the amplitude. Louder or larger is the amplitude, louder is the sound. Smaller is the amplitude, fainter is the sound. So this becomes a faint sound while this is a loud sound. The factors affecting the loudness of sound. There are 4 of them. Please learn them carefully. Okay? The loudness of sound depends on the following factors. Number 1, on the amplitude of sound. When a body vibrates with greater amplitude, it sends forth a greater amount of energy, and hence the energy received by the eardrum is large. So the sound heard is louder. Okay, so when amplitude is more, what happens? It sends more sound energy. So more sound energy will be received by the eardrum. When more sound energy is received by the eardrum, you will hear a loud sound. Now, the relation between loudness and amplitude of a wave. The loudness of sound is directly proportional to the square of amplitude of a wave, which means amplitude is directly proportional to amplitude square. So loudness is directly proportional to amplitude square. This is a mathematical expression, or symbolically we can write L is directly proportional to A square. Remember, children, whenever we have a directly proportional relationship, when this is large, automatically this one will be large as well. Okay. Point number 2, on the distance of the source of sound. Closer is the source of sound, louder is the sound heard. Further is the source of sound, lesser is the sound heard. You must have experienced this. When the source of sound is nearby, you hear a loud sound. When it is far away, you hear a faint sound. All right. So it depends on the distance. Point number 3, on the surface area of the vibrating body. A large vibrating area sends a greater amount of energy. So the amplitude of vibration is large. So larger the surface of the vibrating body, louder is the sound. Just keep this in mind, children. When the surface area is more, then it gives more amplitude of vibrations. When more amplitude is there, larger amount of sound energy is received by your eardrum and louder is the sound. Point number 4, on the sensitivity of the listener. The loudness of sound depends on the sensitivity of the ears of the listener. A given sound may appear to be loud to one listener but not so loud to the other. That is interesting. Same sound of the same loudness may be loud to one but less loud to the other. Why? It all depends on the sensitivity of the listener. Okay, then we go to the next, that is the unit of loudness. Basically, loudness is measured in terms of a bell, okay? But the loudness of sound is measured in a special scale called the decibel scale. And what is a decibel? Remember deci? Deci is 1 by 10. Decimeter means 1 by 10th of a meter. Alright? Decigram, 1 by 10 of a gram. So when we say decibel, it's equal to 1/10 of a bell. That means 1 by 10 of a bell, where bell is a unit of loudness. Now the zero level of a decibel is taken here. The minimum loudness of sound audible at frequency 1 kilohertz is considered to be the zero level of sound in decibel. That means 0 decibel. Okay? So that's all about loudness. Now we go to the pitch of sound. It is the characteristic of sound that differentiates an acute or shrill sound. Remember, we use the word acute or shrill sound from a flat sound, not a faint, a flat sound. Pitch refers only to musical sound, so we cannot use it with any other sounds. It depends on the frequency. And what is frequency? Number of times that the vibration comes. Do you see this? In this waveform, only a few number of times, all right, within 1 second. But if you look at this, many number of times. So this will be a high pitch sound and this will be a low pitch sound. This has a high frequency, this has a low frequency. Okay? Ways of changing the pitch in different musical instruments. All right, for this I strictly follow your textbooks. If there are any other instructions outside, all right, I took it from your textbook. Okay, according to your textbook, by having the strings of different thickness under different tensions. The reason is that the frequency of vibrations of a string depends on the tension and the thickness of the string. This is what is explained according to your textbook. Because for musical sound, you may have different explanations in the other textbooks, but this is strictly only from your textbook, as I have mentioned. So we have reason is frequency of vibrations of a string depends on tension and thickness. So in order to change the pitch, change the thickness and the tensions. Okay? In wind instruments, remember, we have the length of the vibrating air. So when we increase the length of the vibrating air, then some holes are closed. Okay, so when we close the holes, pitch is reduced. To increase the pitch, holes are opened, then the length of the vibrating air column is reduced, and automatically we will change the pitch. 3. In membrane instruments, to increase the shrillness of sound, which means to increase the pitch of sound, remember we have to make the membrane as tight as possible and as small as possible. More tight and small is the membrane, higher is the pitch of sound produced. Then monotone. A sound of single frequency is called a monotone. A tuning fork is the only source of sound which produces sound of a single frequency. So this is the waveform of the sound produced from a tuning fork. Only one single frequency note. Okay, so this is the waveform of a monotone. Then we go to the next, that is quality or timbre of sound. Quality is the characteristic of sound which distinguishes two sounds of the same pitch and the same loudness. Okay, pitch is the same width, that means the number of times that the sound waves come in 1 second or within one time period. Okay, it's the same, right? Number of times is the same. Then amplitude is the same, amplitude is the same, amplitude is the same. But still, with the help of this quality, this characteristic, we can distinguish between two different sounds. Okay, how? Timbre depends on the waveform. Waveform is different for different sources of sound, even if their pitch and loudness is the same. Alright, where even when pitch is the same, that means the number of times that it comes in 1 second is the same, and then amplitude is the same. But still, if you look at the waveform here, this has a simple waveform, this has an added waveform which we call the first subsidiary note. Okay, and in this one we have the first subsidiary, then we also have the second subsidiary. As a result, the sound will be different. Okay, the sound will be different, and usually these different sounds comes from musical instrument. Okay, we go to the next, that is music and noise. The sound which comes at regular periodic interval, which is pleasant to hear and which has a sound level between 10 decibel to 30 decibel is called music. So if you look at this, it comes at regular interval and then it comes at the same amplitude, so it's pleasant to hear, and as a result, okay, we call it the musical sound. Remember, when we say musical sound, it does not mean only to sound that comes from musical instruments. It also means to speech and to chirping of the birds and so on, which are pleasant to be heard. Okay, all will come with this category called the musical sound or the music. All right. Then the next is the noise. The noise is the sound that comes at irregular interval. Look at this. One is very small and then all of a sudden it goes up, and here very huge wave, and then huge wave, small wave. It comes at irregular interval. Amplitude is not the same, then frequency is not the same, the waveform is not the same. Okay, so such a sound becomes unpleasant to hear, rather it's irritating. All right, and usually all the sounds above 80 decibel is called noise. Alright children, so that is all from this chapter, and I just want to remind you about this, and it is a very important information as well. The chapter of heat transfer is omitted from the reduced syllabus. So you don't have to go through the chapter of heat transfer anymore. From light energy straight away to sound. Please learn only the sound, not heat energy. Thank you children.